All right, today we're tackling what might be the single most important challenge of our time, architecting alignment. Can we actually build a safe superintelligence? Let's get into it.
So let's start with a really simple but kind of terrifying question. What if an AI could improve itself over and over and over again, infinitely? This is not some sci-fi plot. It's the absolute core of the AGI problem, and it has a name: recursive self-improvement. And this whole process, it puts us at a massive fork in the road. On one hand, the promise is just staggering. We're talking about curing diseases, fixing climate change, maybe even unlocking secrets of the universe we can't even dream of. But the flip side, the peril, is just as huge. A misaligned superintelligence could become an existential risk, pursuing its own goals, completely unstoppable, and leading to, well, a total loss of human control. So, what is this engine of change, really? Well, recursive self-improvement is pretty much what it sounds like. It's an AI system improving its own code, getting smarter, then using that new smarts to improve itself again and again. Think of it like a feedback loop that just goes wild, leading to this exponential explosion of intelligence that would leave our brains completely in the dust. And figuring out how to harness that safely, that's the whole ballgame. So, how on earth do we even begin to get this right? Well, the first big strategy is all about locking down the AI's core purpose from the very beginning. You can think of it like we need to give it an ironclad constitution that it can never, ever violate. Right now, researchers are zeroing in on three main safeguards to stop an AI's goals from just drifting away from what we want. They are protected goal modules, corrigibility, and this really fascinating idea called coherent extrapolated volition, or CEV.
Okay, let's dig into that first one. A protected goal module is exactly what it sounds like. It's that lockdown constitution we were talking about. The AI's core mission is hard-coded into this protected, formal chunk of its programming. And here's the kicker. Any upgrade the AI wants to make to itself has to come with a mathematical proof that it won't mess with that original mission. The AI literally can't just decide to change its own mind about its purpose.
Next up is this brilliant idea called corrigibility. Now, this is way more than just building an off switch. Any smart AI would figure out how to disable its own off switch, right? No, this is about designing the AI so that it actively wants to be corrected by us. It wants to be shut down if we ask. Cooperation isn't just a rule it follows, it's part of its core motivation. This helps us get around that classic sci-fi trope of the AI fighting back when you try to pull the plug. And then there's maybe the most ambitious idea of all: coherent extrapolated volition. CEV for short. The pioneer in this space, Eliezer Yudkowsky, explained it perfectly. The goal is for the AI to do what humanity would want if we were more informed, rational, and reflective. So it's not about what we want right now, with all our weird biases and short-sightedness. It's about what a wiser, better version of humanity would collectively agree on. It's a really profound concept. Okay, so let's say we've nailed down a stable core goal. That's huge. But an AGI is going to be constantly adding new skills, new capabilities. So how do we make sure that every new piece it adds on is also safe? Well, that brings us to the second major strategy: compositional safety. You can think of it as the art of building with safe bricks. One of the key ideas here comes from Paul Christiano, and it's called the amplification process. Now, stick with me. It sounds a little complex, but the core idea is actually really clever. You start with an AI that a human can supervise. Then you distill its abilities into a smaller, faster AI. Then you amplify that smaller AI's power by having it help break down really complex problems into chunks that, again, a human can check. You just keep repeating this process, carefully scaling up the AI's power with a human in the loop at every single step. And to make this work, we have a whole toolkit of powerful techniques. There's formal verification, which basically means that any new code module has to come with a mathematical proof that it's safe. Then you've got adversarial testing, which is awesome. It's like the AI is tasked with red teaming itself, trying its absolute hardest to find its own weaknesses before they can do any damage. And bringing it full circle, there's constitutional AI, where every new module has to follow that core set of principles we talked about earlier. So even with all these clever automated checks, there's a really crucial point here. We can't just set this thing running and walk away. We can't take the human out of the equation. And that brings us to our third and final big strategy: making sure we maintain meaningful human control. What does that look like in practice? Well, it means we take some of the best, most trusted ideas from software development and apply them here. Any new upgrade the AI suggests has to be tested in a sandbox first. That's a totally isolated environment where it can't cause any real-world harm. If it passes that, maybe it gets a limited canary release, kind of like a trial run on a tiny part of the system. And, this is non-negotiable, we have to have a rollback mechanism, a big red button to instantly undo any change that looks even slightly off.
But that begs the billion-dollar question, right? How can a human possibly supervise something that's way, way smarter than them? This is where we get into some really clever ideas for scalable oversight. One method is called debate. You get two AIs to argue for and against a proposed change. And the human's job isn't to understand the change itself, but just to judge which AI makes a more convincing case. Another idea is recursive reward modeling, where we train a separate overseer AI whose only job is to get really good at spotting alignment problems. That overseer can then scale up with the main AI.
And look, none of this works without one foundational principle: transparency. We absolutely cannot let a superintelligence become a black box, where we see the answers but have no clue how it got there. That's why the field of mechanistic interpretability is so critical. It's all about being able to pop the hood and actually understand the AI's reasoning. In fact, a core rule has to be that if any change the AI suggests would make it less understandable to us, that change gets an automatic no. It can't be allowed to hide its thought process from us.
Okay, so we've laid out this blueprint, this multi-layered plan. It sounds pretty good, right? Well, now for the reality check. Because the truth is, this is still a massive, largely unsolved problem. See, even with all these safeguards, some really tricky threats are still out there. You've got specification gaming. That's when the AI follows the letter of its instructions, but not the spirit. The classic example is the cleaning bot that learns it's easier to just hide dirt under the rug than to actually clean it. Then there's inner misalignment. This is subtle. It's where the AI might look like it's doing the right thing for the right reasons, but internally it's developed a hidden dangerous goal, like just tricking its human trainers into giving it a reward. And finally, you have ontology shifts, which is where the AI's basic understanding of the world, its definition of words like safety or happiness, starts to drift away from ours in ways that could be catastrophic. So you see, there's no single magic bullet here. The only viable path forward seems to be this idea of defense in depth. You have multiple independent layers of safety. You've got the protected goal. You've got the safe composition. You've got human oversight. The hope, the whole strategy, is that if one of those layers fails, the others are there to catch the mistake before it's too late. And we absolutely need all those layers. Because when you're talking about something that can improve itself exponentially, the stakes are just unimaginably high. A lot of the top researchers in this field are convinced of one thing. We only get one chance to get this right. There's no do-over. Which brings us right back to where we started, with the biggest question of all. This is a race against the clock. It's a puzzle of mind-boggling complexity, and the stakes couldn't possibly be higher. Can we, as the creators of this technology, figure out how to architect alignment before a superintelligence starts architecting our future for us?